guys. So, hopefully you all had a good spring break. Week off. We're getting right back into it. Yeah. We have two main chapters left, Chapter 6 and Chapter 5. Chapter 6, what we're covering here is exponential and logarithmic functions. Exponential and logarithmics are inverses of each other. They undo each other. So if we apply a logarithmic to an exponential, they will cancel each other out. They'll simplify each other out. So they are inverse functions. Now, what we're doing first is chapter 6.1 and 6.2. We're doing two sections in one because really I don't think either one of them deserves a full day up by themselves. There's a lot we can get into it. When we talk about exponential function, exponential growth, it is defined by the function f of x equals b to the x, where b is greater than 1. Is the parent function of the family of every exponential function we can have. So f of x equals b to the x, and b is greater than 1, it is considered exponential growth. If b is greater than 1,
You want to write that?
or at least highlight it, exponential growth. Because the big thing with exponential growth is that b is greater than 1. If b is greater than 1, it's exponential growth. And we consider this to be exponential growth because the amount that a function increases as x increases for the given function is going to be more and more as we go further along. So if we use, say, f of x equals 3 to the x, this would be considered exponential growth because our base b is bigger than 1. And if we looked at this, and the reason it's exponential growth, if x is 0, so we're saying 3 to the 0 power, you don't have to write this down. Anything to the 0 power is 1. So when x is 1, the y values, or x is 0, y is 1. Now when x is 1, it'd be 3 to the first, which is just 3. And so far, all we've done is increase from 1 to 3. We've increased by 2. Now, when x is 2, we're looking at 3 to the second, 3 squared, which is 9. Okay, we've increased by 3. Now, 3 to the third power is going to be 27. 3 to the fourth is 81. 3 to the fifth power is going to be 240. So as we can see here, we increased by 2, 6, 18, and that would be 54. If we're noticing or starting to notice, the amount that we're increasing is increasing faster and faster. That's why we call this exponential growth. Because if we go to the 9th power, 3 to the 9th power, we're looking at 19,683. This gets bigger and bigger. This is why we consider it to be exponential growth. One of the other things with exponential growth is that it cannot be equal to 0. There's no way I can take a number and put it to a power and get it to be 0. It just does not work. So we call it an asymptote. And the graph rises from left to right, and it will intersect the y-axis at the point 1, 0. Exponential decay. We consider a function to be exponential decay in the form of b to the x if that value of b is between 0 and 1. So if b is between 0 and 1, it's going to be exponential. I need to rewrite that. I'm adding an extra t. So if that power, or that base of b, if that number where b is at is between 0 and 1, it's exponential decay. Because we're multiplying that number by itself that many times. So if it's fractional, 1/2, if we square it, 1/2 times 1/2 is going to be 1/4. It's gotten smaller. We multiply 1/4 by 1/2. So we cube it. It's going to become 1/8, 1/16, 1/32, 1/64. That number is getting smaller and smaller as we go to the right. However, as we go to the left, we put it to negative exponents, it's going to get bigger. So exponential decay is going to decrease as we go from left to right. Exponential decay, as we actually have it in the natural sciences, is half-life. Half-life radioactive decay is exponential decay. Those are those exponential decay functions. That's half-life. That's where that shows up. Especially exponential growth. How we track wind speeds for hurricanes, earthquakes is in the same form. Just because it goes up from a category 1 to a category 2, it doesn't feel like it should be that big of a jump, but we track it by exponential growth. Now, next thing we're looking at. Okay. They gave us an equation. This here. We need to, 1, determine whether it's exponential growth or exponential decay. And then 2, we need to evaluate it when x is 2. So y equals 2 to the x. Exponential growth, exponential decay, in the general form is y equals b to the x. So for this first one here, for a, what is the value of b? 2. Is 2 greater than 1 or between 0 and 1? So it has to be growth. Now we also need to figure out what the value is when x is 2. To the second power. I'd grab the calculator. I'd still do it along with me. 2 squared is so we know that when x is 2, y value is 4. So you can say y equals 4. Or we can just circle the 4 either one. But again, as that x value, that value of x increases for this function, that number is going to get very big very quickly. Questions on number 1? Or letter A. Questions on, are you ready for B? So y equals 1/2 to the x. What is our base? What's the value b? 1/2. Is that greater than 1 or between 0 and 1? Between 0 and 1, so this is decay. It's going to be a decay function. Because that value of b is between 0 and 1, it's going to be decay. It's going to be going down. Now we need to figure out what value of y is when x is 2. And again, we can grab the calculator, go parentheses 1/2, close parentheses, equals 1/4, or 1/4. All right, guys. Questions on these two here? Y equals 1.3 to the x. Would this be growth or decay? It's greater than 1. So even though we do have a decimal, if that value of b, since it's 1.3, since it's greater than 1, it's going to be growth. Doesn't matter what form they give it to us in or what form they write it in. If it's greater than 1, it's growth. Yes. Yeah. Questions on this here? Let's look at B. Y equals 1/3 to the x. This would be decay. Now you do need to be careful. Just because it gives us a fraction doesn't necessarily mean it's going to be decay. This one is because that fraction 1/3 is between 0 and 1. So 1/3 squared is, yep. Interestingly enough, if we took 1/3 and put it to the negative second power, it'd be nice. Questions on these here? On the next ones? Now, the next set of 4, I'm not so focused on evaluating. We're just going to determine if it's growth or decay. So the first one here, y equals 4 to the x. It's growth because the base is 4, which is greater than 1, so it's growth. Number 2.
Well, it's more than 1. It's 2/3. It's not a whole number.
So if we're not sure, so 2/3, 2 is greater than 1, but because the numerator is smaller than the denominator, the top of the fraction smaller than the bottom, it's actually 0.6666 repeated. So it's less than 1. So sometimes it might be easier. No. So one of the big things, if you're not sure, especially with fractions, throw them in the calculator, convert them to a decimal. Because that's sometimes easier to see as a decimal than it is as a fraction. So it is between 0 and 1, so this would be decay. F of x equals 0.25 to the x. 0.25 is our base.
That's decay.
Since it's smaller than 1, it is decay. Number 4, f of x equals 1.5. 1.5 is bigger than 1, so it is growth. Questions on these 4 here? Now the other one that we have is natural logs. So natural logs deal with the exponential function with base e. E is just a number. E is an irrational number. E is this here, 2.718281828846, and it continues on indefinitely. It's an irrational number. And this here is actually the exponential function, or just the value of e, or how we would find it. Now, when we look at e, just like pi, and most of our irrational numbers, we can almost treat it like a variable and how it works. So if I said I had e to the third power times e to the sixth, if this was, say, x to the third times x to the sixth, we are multiplying like bases, so we can add the exponents. E to the 3 plus 6, which is e to the 5. We can treat it almost like we do a variable, but the main difference is that this e has a value, has a specific value. So if we look at 16e to the 5th divided by 4e to the 4th, we can divide our numbers first. We can simplify those numbers first. 16 over 4 is just going to be 4. E to the 5th divided by e to the 4th. When we divide like bases, we subtract the exponents. So 5 minus 4 is 1. Since it's bigger on top, it will stay on top. So it's 4e. Questions on the first two? Powers of powers multiply. So 3e to the negative 4x squared, so we're going to have to apply that power to both.
The exponent also.
So for our 3, we would apply this because it's 2 times 1, which is 2, times our e to the negative 4x times 2. Powers of powers, multiply.
Wouldn't it be 60? Or 60?
I didn't multiply out just yet. Now our 3 squared, 3 times 3 is 9. E to the negative 4x times 2, negative 4 times 2 is? Powers of powers multiply. Now the 3 is really 3 to the first. So we multiply it by 2, 3 to the 1 times 2, which is 3 squared. E to the negative 4x, we're going to multiply by that power of 2, giving us e to the negative 4x times 2. Negative 4 times 2, negative 8. So e to the negative 8x. Questions on this here? We cannot leave exponents negative. So to make it positive, we have to move it from the top of the fraction to the bottom. So we have to move the e to the 8, negative 8x, down to the bottom of the fraction, which is going to make that exponent positive, just the exponent. Now, since the 9 did not have a negative exponent connected to it or with it, it stays on top. Questions on this here? Any questions on A, B, C? Now we're going to look at 1, 2, 3. We're going to come back to problem D and problem 4 in a minute. Let's look at number 1. E to the 7th times e to the 4th would be, since we're multiplying like bases, we can add the exponents. So we'd have 7 plus 4, which is 11.
Wait, why do we add them instead of
So when we're multiplying like bases, we add the exponents because you don't have to write this part out. Really what we're saying, e to the 7th, I'm multiplying e by itself 3, 4, 5, 6, 7 times. That's just e to the 7th. And I'm multiplying it by e to the 4th. So I'm saying that I have another 1, 2, 3, 4 e's being multiplied together. That's all an exponent is. Exponent says I'm multiplying that term by itself this many times. Well, how many e's do we have total? Here I have 7, 4, so we have a total of 11, yes? So we feel good with that there, yes? So we're multiplying like bases. When the bases are the same, they're both e and e, we can add the exponents together because I have 7 of them, multiplying it with 4 more, saying I have a total of 11. And we multiply like bases, we add those exponents. Powers of powers, when we're putting an expression to a power, like number 3, we multiply those exponents together. Because really what this is saying is we're multiplying it by itself 3 times. So the other way to do this, and you don't have to write this, and that should be E. Because cubing that expression, saying we're multiplying that whole expression by itself 3 times. Which I have 10 times 10 times 10. Really is 10 to the 3rd. Here I have e to the negative 3x plus e negative 3x. Because I'm multiplying like bases, we get all these 3x being added together. Well, negative 3x plus negative 3x plus negative 3x. Would that be the same as just if we'd have said negative 3x times 3? Because I have 3 of them being added together. That's that power of powers. And well, 10 to the 3rd, all right guys, focus in, is 1,000. That part's nice. negative 3x times 3, negative 3 times 3 is negative 9x. Since that exponent's negative, we got to move it from the top of the fraction to the bottom. And that's it. And it's kind of nice that even though it is an irrational number, we can treat it almost the way we would variables. 1,000. I said 1,000 and wrote 100. Thank you. So.
Okay, so you do 24 divided by 8, right? That's
20.
your 3. Then you put your e. What do I do with the 8 and the 5?
So 24 over 8 is indeed 3. We divide those. When we divide like bases, we subtract the exponents.
So 8 minus 5 times e to the third power.
And because it is bigger, we have more e's on top. It's going to stay on top. If the e to the 5th had been on top, e to the 8th had been on bottom, put it on bottom.
Yeah.
On bottom of the fraction.
Can you go back down, please?
Wait, is that 1,000 or?
It should be.
It should be 1,000.
The one like above the fraction.
Yeah, it's 1,000.
It's 1,000 e. Let's clean that up. 1,000. We ready?
You're multiplying, then you add, and if you're dividing, you subtract.
Yes. Because when we multiply, we're really just adding them together. We have more. When we divide, I'm simplifying one of them on top and bottom, so they're being removed. Any other questions on ABC or 1, 2, 3?
No.
Letter D, square root of 16 e to the 4x. We're going to break this into two parts. Our square root of 16 times our square root of e to the 4x. With our radicals, our square roots, we kind of covered this in Algebra 1, talked about it some in geometry here and there when it did show up. When we take the square root of something, or take a radical, properties of radicals say if I have two or more things being multiplied inside the radical, I can rewrite it as a product of those radicals. The reason we do this is because, say, the square root of 16, as we have here, square root of 16 is just saying what times itself is 16, and we know that is 4. That we know. Now the square root of e to the 4x, we're trying to see what times itself gives us e to the 4x. Well, we don't know. And one property that we have, and we'll talk about it more later in the year, is this here. The nth root of a to the x. So whatever root we have, that's all n is just a number, an integer number. And normally we don't talk about negatives, so it's really the positive integers if we want to be technical. So we take the nth root of a to the x power. This, by definition, is equal to a to the x over n, a fractional exponent. And this is actually very nice, it's very neat, and is actually that's something that is very useful. Because our square root of 14, or not square root of 14, square root of 16. Well, 16 is just 4 squared. We can agree with that, yes? So according to this here, since we're talking about a square root, even though we don't write it, the index is understood to be 2. So according to this property here, our base is 4, because that's what a is. A is 4. The nth root of a to the x is equal to a to the x over n. X is the exponent attached to that number. So the exponent in our case is 2. N is the vertex, or the index. What's inside that v? Guys, focus up. Focus up. And what's inside our index, or what our index is inside that v is 2. So really the square root of 4 squared in exponential form is 4 to the 2 halves. So if we don't leave a fraction as 2 halves, it is 1. So we're really saying that we have 4 to the first power, or just 4. That's why when that index and the exponents match, they simplify out, they cancel out. So to convert it to exponential form, exponent goes on top, index goes on bottom. So if we look back at D, e, the square root of e to the 4x. The number inside that base is still e, but the exponent attached to e is going to go on top of the fraction. And the exponent is what?
4.
And x. And our index, even though we didn't write it, since it's a square root, is 2. So the square root of e to the 4x as a exponent is e to the 4x over 2.
Is that always going to be a 2 right there?
As long as it's a square root. So on number 4, the index is 3 because it's a cubed root.
So it would be whatever 9x over 3.
Yes. Now 4x over 2, 4 divided by 2 is what? 2. So this is e to the 2x. So really, we just took that exponent and divided it by 2. Any questions on D before we look at 4? So the cube root of 64 is what we're looking for first.
Oh, cube root, just joking.
So square root would be 8. But if we want to look at the cubed root of 64, it is 4. Because 4 to the third power is indeed 64. So the cubed root of 64 is 4. Now our cubed root of e to the 9x. So they write it as an exponential so we can see how this reduces. We take the exponent attached to e, that 9x, and put it in the top of the fraction. It's our x. And the index is 3 in this case because it's a cubed root, so it's 9x over 3. And it would indeed be 4e to the 3x.
Easier than the first one.
Now this is as deep as we are going to go with these converting radicals to exponentials and kind of trying to simplify form for the most part. Questions on these here? We ready for the last piece?
Yeah.
Now, these functions with base e can be defined as exponential growth or exponential decay. Equals, I think it's r, I think they're defined as r, or ae to the rx. So the one to the left is our growth e to the x. The one on the right is e to the negative x. So with exponential growth and exponential decay, where e is the base, we're looking at what the exponent is, not so much e itself. Because e is defined to be an irrational number. So it's 2.7 going on. So there's nothing we can do with it. It is positive. Now, as they showed this here, e to the x, what's a positive number to an exponent? It's just going to get bigger and bigger. Since the base is greater than 1, exponential growth. Now, the reason we consider e to a negative exponent to be decay So y equals e to the negative x. So negative a, I'm going to just put an a in there, just to kind of drive this point home, because a could be whatever we want, any real number. But if a base is put to a negative exponent, if an exponent's negative, for us to be able to make it positive, we've got to move it from the top of the fraction to the bottom. So really what they're saying is y is equal to 1 over e to the ax, or 1 over e to the x. That means that base is now between 0 and 1. It is decay. So really, when we see that that base is e, I'm not so much looking at what the number is. I'm looking at the exponent. So this first one here, e, 3e to the x. 3 is not telling us anything. It would be, it's growth, because the exponent here is positive. So b would be decay because that exponent attached to it is negative.
Now that one would be decay also.
It's gross because x equals 1, greater than 1.
So it's not so much, it is greater, but it is positive because that exponent's positive.
And the negative x, that's negative 1, so that's decay.
Mm-hmm.
Rather than 2x is growth because it's whatever 2x is.
Yes, so when we look at this here, it's not so much the number, it's the sign. If it's negative, it's decay. If it's positive, it's growth. So with these e, when the base is e, if that exponent's positive, it's growth. If that exponent's negative, it is decay. Questions on these here?
Oh! Scumbag!
I'm going to give y'all 3 so you can pass one back.
Oh, appreciate it.
Y'all could get probably most, if not all of this done before the bell. You're welcome. So questions 1 through 4. Evaluate each of these. Figure out what the value would be when x is negative 2 and x is 3. So you're just replacing x with negative 2 and x with 3 to get those values.
Wait, how's x gonna be two numbers? Oh, wait, you want us to do one if it was
So
negative 2 or if it was positive, or if it was positive 3?
the first one,
It would be 1/4 and 8.
1/4 and 8. So you're just evaluating, you're plugging that value of negative 2 in for x and seeing what the number is. Doing it again when x is 3, so you'll have 2 different answers. 5 through 14. Determine if each function is either exponential growth or decay. So 5 through 14, you're saying growth or decay. That's it. 15 through 18 on the back. Simplify like we did with e. So multiplying, dividing, or simplifying down, simplifying those powers, products, radicals. And lastly, 19 through 24, determine or tell whether the function represents exponential growth or decay. So you're just saying growth, decay. That's it.